All right, chapter 11, liquid and intermolecular forces, right? So states of matter. We talked about states of matter, right, in previous chapter. And you have a gas, liquid, and solid. So the states of a substance is at a particular temperature and pressure depends in two conditions, in two entities. Kinetic energy of particles and the strength of the attraction between the particles, right? So have here the physical states, the states of matter, gas, liquid, and solid. The gas assumes both volume and shape of its container. The liquid assumes shape of a portion of its container, right? But the volume is fixed, right, for liquid. And solid retains on shape and volume. That means solid has fixed volume and fixed shape, right? The gas expands to fill its container, and the liquid and solid does not expand to fill its containers, right? Because here, the volume for liquid and solid, right, is fixed above. The gas is compressible, right? And liquid and solid, we consider is virtually incompressible, actually, right? Gas flows readily, right? And liquid flow also can flow, right? Like, and solid does not flow. And related to diffusion here, diffusion in a gas occurs rapidly, right? And the diffusion in a liquid occurs slowly. In the solid, diffusion extremely slow. Right. Let's say chapter 11, right? And here, I was in chapter 12. Chapter 12 is only this portion about chapter 12. This is why the active homework has only 6 questions for chapter 12. Chapter 12 will be only about this portion here. That's about the types and properties of solid. Only this portion here. So crystalline solid, you have crystalline solid and amorphous solid. So crystalline solid is a solid in which the particles are arranged in a definite repeating pattern. That means they are organized for crystalline solid. And amorphous solid is a solid in which particles lack an organized structure. That means this one here is not organized, the structure. So in relation to the solids, you have ionic, molecular, metallic, and network. So the ionic solids, they have ionic interaction, right? Ionic bonding, and they have the ionic, we saw, right, in the previous chapter, that they have like high melting point, high boiling point, and it's hard. For example, here, sodium chloride and magnesium oxide, that here you have, right, metals and the non-metals here. Oops. Metals and non-metal from sodium, metal, chlorine, non-metal, magnesium, metal, oxygen, non-metal. And then here you have molecular solids. Molecular solids, it's the interaction here is a covalent bonding. The intermolecular force, the bonding will be covalent bonding. And interaction is hydrogen bonding, dipole, and the long dispersion. Talk more about it, gonna be here. I'm gonna talk about that soon here. So covalent bonding is intermolecular force because bonding in a molecule, right, between atoms. But here you have intermolecular force because it's forces between molecules. In molecular solids, they have low melting point and they are no conducting. For example, hydrogen and carbon dioxide. Metallic solids they have metallic bonding, right? They have metals with metals. And the properties here, they have variable hardness and melting point. And the metals, right, they are good conductors. Example here, iron and magnesium. So network. Network is still covalent bonding, is between no metals, for example. But this one has high melting point, they are hard and no conducting. For example, here, the molecular one here has low melt point, but network, the special, is still covalent bonding and between high melting points, right? For example, here we have the solids. They extend networks of ions hold together by ion interactions here. Molecular solids, right? This one, the stacked molecules are held together by intermolecular forces. And the metallic solids, the extend networks of ions hold together by metallic bonding, right here, metals with metals. In this one that's gonna be new, right? You have covalent network solids. I mean, you have like the covalent bonding between here, but they are continuing extending. I've seen here that are continuing more atoms here, more bonding, more interactions here. So it's very large structure, like connection here. And we call covalent network. The extended networks of atoms hold together by covalent bonds, for example, carbon and silicon, right? So, and then here, most common allotropes of carbon. Allotropes are different structural forms of the same element. For example, here you have carbon, diamond is the atoms here is carbon, and graphite is also carbon. But what's different here is how they are organized here. The structural forms here. But and it's in the definition of allotropes, right? Are different structural forms of the same element. So this is the only thing about chapter 12 that you needed to know. Now, let's go here. Go back to chapter 11. So yeah, so with this handout here is for all sections. So we have all sections have the same handout. So all of the professors also do the same thing here. Chapter 11 start, then talk a little bit about chapter 12, and then go back to chapter 11. Right? Okay. States of matter, right? We talked about that they have the gas, liquid, and solid. You can see here in the gas, the particles, they are very far from each other, right? And the liquids, they are getting closer. And the solids, they are very, very close, right? The particles here. So the fundamental difference between states of matter is the strength of intermolecular forces of attraction. So stronger forces bring molecule closer together, right? So kinetic energy keeps them apart and moving. Remember that every kinetic energy is related to temperature, right? Higher the temperature, higher will be the kinetic energy. So because in solid and a liquid, states of particles are closer together and refer to them as condensed phases. Okay, so now let's talk about intermolecular forces, right? So before we talked about, in the previous chapter, about covalent, ionic, right? Covalent and ionic, they are forces, they are like intra because intramolecular force because the force inside the molecule, right? Because it's for bonds, covalent bonds, ionic bondings. But intermolecular forces is between molecules. So he is in the same molecules and he is between different molecules. So the attractions to molecular force are the attractions between molecules and are not nearly as strong as the intramolecular attractions that hold the compounds together. Right? He's talking about the bonds, covalent bondings, ionic bonds. In these intermolecular attractions, however, they are strong enough to control physical properties such as boiling and melting points, vapor pressure, and viscosities. Right? Are you seeing here? So we have here 2 molecules of HCl. So the bond between here inside the molecule is a strong intermolecular attraction. This one is a covalent bonding. The same thing with this molecule here, right? This line here. Everything we have the dots. The dots here, they are represent intermolecular attractions. And actually, this one, they are weak intermolecular attraction. They're weaker than this attraction here. Okay, right. But how do you know? So we're gonna study soon. How do you know what's gonna be the difference between the kinds of intermolecular forces, right? So types of intermolecular force between neutral molecules. The first one, dispersion forces, also known as London dispersion forces, or induced dipole attractions. So this one in here. So the dispersion forces, they are temporary attractive force that occurs when electron clouds and neighboring atoms occupy positions that create temporary dipoles. For example, here, we have atom A and atom B, right? So they have temporary dipoles. For example, this A sometimes will be the positive and the B sometimes will be the negative. Sometimes they switch here, right? Because they have temporary dipoles. They keep changing. And the tendency of an electron cloud to distort is called polarizability. And these forces are present in all molecules. So all molecules they have dispersion forces. And what are dispersion forces? The dispersion forces, they are the temporary attraction forces, right? So these forces are present in all molecules, like polar or non-polar, they're still going to be there for all molecules. And the factors that affect the amount of dispersion forces in a molecule are the number of electrons in an atom, so more electron, more dispersion forces, and the size of an atom or molecule. So larger the molecule or mass, larger will be the dispersion forces. In the shape of molecule with similar masses, more compact the molecule is, like the shape, will have less dispersion forces. Right. So linear, so we have here 2 molecules. This molecule here, an example. In this one here, linear molecule, larger the surface area, enhances intermolecular contacts and increase the dispersion force, right? This one here is more compact, right? The shape here, spherical molecule. So smaller surface area diminishes intermolecular contact and it decreases dispersion force, right? So here is larger surface, increase dispersion forces, and here smaller surface, so decreases the dispersion forces here, right? So dispersion forces, they are the all molecules, they have dispersion forces, right? But not all molecules, they have dipole-dipole. Okay. Dipole-dipole forces are forces that they have permanent dipoles. That means one poles on one, like for example here, hydrochloric acid. So the hydrogen will be always the positive, and the chlorine also gonna be the negative dipole. So here you have a fixed, a permanent dipoles here. So polar molecules have a more positive right side and more negative ending. So we have here we call dipole. And the oppositely charged ends attract each other. So here, right? So for example, here you have the the molecules here of the solid right here. And then the dots, they represent the attractive dipole-dipole interactions here. These two, right? So, but this dipole-dipole force is when we have permanent dipoles. But all molecules, they have also what? The special force. For example, here, hydrochloric acid is a molecule that they have dipole-dipole, right? But also has what? The special forces. Okay? Okay, right. So, and then for molecules of about equal mass and size, more polar the molecules, the higher is its boiling point, right? So here is increase the polarity. So the interactions with dipole also increases here, increase. Okay, so molecules of similar size, so the more polar, right, the molecule, the higher its boiling point. The higher its boiling point here. So in the polar molecule have the dipole-dipole will increase. So dipole-dipole interactions, right? They are when you have a permanent poles and they are stronger than the special force. So, for example, here, hydrochloric acid. Which one, you have the two interactions, right? But which one is the stronger dipole-dipole? That means the dipole-dipole be the dominant intermolecular forces here, right? So the more polar the molecule, the higher is its boiling point. So the dipole here, right? Interactions will likely be the dominant one in your case. And so here, even though they are the same size, you're gonna say, okay, they are the same size, but which one's more polar, right? So if we are the same size, but the one that it has higher polarity, right, will be stronger one. And about molecules of different size, the dispersion forces will likely like determine, right? Its physical properties. Right? And we saw here, so smaller the surface area, right? Decrease the dispersion forces. So the larger the molecule, the larger the surface area, you have higher dispersion forces. So here. So the molecule of different size, the larger one, oops, the largest one will be the strong one, the stronger. Okay. Now, talking about the special forces, about dipole-dipole, now let's talk about hydrogen bonding. Hydrogen bonding is a special kind of dipole-dipole forces. So, but while this one is different, because this one is a dipole-dipole when you have a hydrogen, right, interact with fluorine, oxygen, or nitrogen. So dipole-dipole interactions, they have, is when you have a hydrogen bonded to nitrogen, oxygen, or fluorine. They are very strong here, these interactions. Why they are very strong? Because of the electronegativity difference here. Like a hydrogen bond is interaction between a hydrogen atom attached to a highly electronegatory atom, right? And fluorine, oxygen, and nitrogen, they have a high electronegativity. So this electronegativity difference here, you make a very high difference. So we make the hydrogen bonding stronger than a normal like dipole-dipole, right here. So here, so when you have, for example, water, right, H2O, you have covalent bonding between in a molecule, right? We have equivalent bonding here. This is when the bond enter like in a molecule. And then, are you seeing the dots here? They represent the intermolecular forces. And that case here is between what? Oxygen and hydrogen. So this intermolecular force here, we call hydrogen bond, right? Intermolecular force. And the last kind of the molecular forces here is the ion dipole force. So this one here, the ion dipole interactions is the fourth type of force that are important in solutions of ions. And the strength of these forces is what makes it possible for ionic substance to dissolve in polar solvents. So, for example, we have sodium chloride. Sodium chloride, right? When you dissolve sodium chloride in water, it will dissociate between sodium plus and Cl minus. So why do they dissociate here? Because the interaction between sodium ion and water and the chlorine and water, right? These interactions here, they are stronger than the interaction between sodium and chlorine. That's why when sodium chloride, they are in water, they dissociate it into sodium plus and chlorine minus here. So you see here, sodium plus around water, right? Intermolecular force with water. The same thing, chlorine, the chloride ion here, doing intermolecular forces with the water here, right? So the positive ends of polar molecules are oriented toward the negative charged atom, like the case here, right? The hydrogen are the positive one, and they are doing intermolecular force with chlorine, that's the negative one, right here. But for sodium plus, that's the positive one, the oxygen that's doing the connection, the intermolecular forces here, right? The oxygen that it has the negative dipole, right? So negative with positive, positive with negative. Okay, but how to classify which one is which, right? So here, this table here explains very well. Let's see if I can get closer. Oh no, it's not getting better. Okay, right? So here, type of intermolecular interactions. Which molecules will have dispersion forces? The answer is all. Doesn't matter if only atoms, non-polar molecules, polar molecules, or polar molecules with hydrogen bonding and ionic solids. All these molecules here, they have dispersion forces, right? But which one has dipole-dipole interactions? Only the polar molecules, right? And then the polar molecules that the ones that have hydrogen bonding, which hydrogen bonded, a hydrogen with what? Fluorine, oxygen, and nitrogen groups, right? Okay, and then the next one. Do we have a dipole-dipole in ionic solids dissolved in polar liquids? You're going to say no here, right? Because you are using ionic solid dissolved in polar liquids. The only interactions here will be dispersion forces and ion dipole interactions here when I use these conditions. Next, go to the next one. Hydrogen bonding. Which molecules have hydrogen bonding? Only the ones that have hydrogen with oxygen, fluorine, and nitrogen, right? So here only is in, you have it here. And then, which molecules have ion dipole interactions? Only when you have ionic solids dissolved in polar liquids like sodium chloride and in water, right? Okay, this is how we're gonna classify here. Okay, so properties that are affected by intermolecular forces. We have boiling point, like higher the dispersion forces, like the higher will be the boiling point and melting point. Not in the special force, actually, higher the intermolecular force, right? Viscosity. So viscosity is the resistance of a liquid to flow is called viscosity. So the viscosity increases with stronger intermolecular forces and decrease with higher temperature. That makes sense, right? That like if they are stronger here, the resistance to flow will be smaller. They'll have more resistance to flow here. Stronger than the molecular forces, the resistance to flow will increase. And surface tension is the energy or work required to increase the surface area of a liquid due to intermolecular forces. So water acts as if it is a skin or like on it to do extra inward forces on its surfaces. And the surface tension, it causes water to build up when it contacts with nonpolar surfaces, right? So one thing important to remember, there is polar dissolves in polar, and nonpolar dissolves in nonpolar. But polar does not dissolve in nonpolar. So that's why I'd say it causes water to build up like when in contact with nonpolar surface, because they will not be like dissolving each other. Cause a surface tension. Then we have here capillary action. Capillary action here. The rise of a liquid upon narrow tubes is called capillary action. So the intermolecular forces that bind similar molecules to one another are called cohesive forces. In intermolecular forces that bind a substance to a surface are called adhesive forces, right? So water has strong adhesive forces with glass. So mercury has a stronger cohesive forces with itself. Like mercury, like is the only metal that's liquid, and like if you have you can see if you see the liquid, the mercury moving, they are very cohesive. They keep it together, like moving but still together. Right. Okay. Okay, so here, let's work with this example here. Which one will have the highest boiling point? So it depends the kind of intermolecular forces here, right? So the first one, so all molecules will have a dispersion forces here, right? But which ones would have only dispersion forces here? So boron chloride is ionic, so you know we also have a dipole, right? Hydrogen here is with hydrogen one with itself. So yeah, this one has only dispersion forces. Carbon dioxide, carbon oxide here, they have a CO here, and then hydrogen fluoride is up, they have a different polarity here, right? They have boiling point, hydrogen bonding. So this one also only dispersion forces. And then neon here also only dispersion forces. So we have three with dispersion forces only. Which one has lower boiling point? They're going to be about the size, right? So helium or hydrogen here is only, each hydrogen is just 1 grams per mole, right? So hydrogen is the smallest one. So the boiling point for hydrogen, right, to be the smallest one, is the smallest molecule between the one that they have with only the special forces. Then the next one is neon. Why neon? If you look at the molar mass for neon, right? So we see the that's higher. The molar mass of neon is higher than hydrogen, but below than carbon dioxide. So the next would be neon here. The neon has a lowest boiling point than carbon dioxide. Sorry, carbon monoxide. So here, all these three has only the special forces. This one here, they have only. Then the next one, let's talk about barium chloride, right? And HF here. Which one comes for us? Okay, so HF, right? And barium chloride here. So they both they have the special force also, and both they are dipole, right? Here. And now let's connect it with the rate, the size, like the HF and barium chloride here. They have the HF has lower molar mass than barium chloride. So this one has a boiling point, has a hydrogen bond, right? That makes us very strong here. But if you compare with barium chloride, so this one has very high molar mass than this one. So the next one, you're gonna be HF, and then barium chloride here. Right? Okay. Phases, so changing, right? Phase changes. Conversion of one state of matter to another is called phase change. So have it here. From solid to liquid is called, right, melting or fusion. From liquid to gas is called vaporization. And then they will come back, right? From gas to liquid is called condensation. And then from liquid to solid is called freezing. Then when you go directly from solid to gas, it's called condensation. And you go directly from, sorry, it's called sublimation here. Right? From solid to gas, it's called sublimation. And from gas to solid is called deposition. Deposition, right? From gas to solid. So when it are happening, like the phase they are changing, energy is either added or released in a change. So the phase change is like melting, freezing, vaporizing, condensing, and subliming and depositing here, right? What involve heating, energy, added or released. The heat enthalpy of a fusion, right, is the energy required to change a solid at its melting to a liquid. And heat of vaporization is the heat energy required to change a liquid at its boiling point to a gas. And the heat of sublimation is the energy required to change a solid directly to a gas. So vapor pressure, how intermolecular forces affect these properties. So at any temperature, some liquid molecules have enough energy to escape the surface and becomes a gas. And as the temperature rises, the fraction of molecules that they have enough energy to break free increases. And as the more molecules escape the liquid, the pressure they exert increases, right? Okay, so in the liquid vapor reach a state of dynamic equilibrium, the liquid molecules evaporate and the vapor molecules condense at the same rate. Okay, so you have it here. Fraction molecules and kinetic energy, right? So here, see, right? Lower the temperature here. So have here the lower kinetic energy. And when the temperature increases, you have a high kinetic energy. Right. So the boiling point is the liquid is a liquid as the pressure at which its boiling pressure equals atmospheric pressure should change from liquid to vapor, right? And the normal boiling point is the temperature at which its vapor is, the vapor pressure is 760 torr, like from torr to atm, right? Is actually is equal to 1 atm. So here, label with 1 or 2 for indoor or exo, and 2 to say which heat equation to use. Okay. Let's label here. This first one, IC heating, that means it's adding heating, right? So gonna be what here? Indoor or exo. So heat is being added, right? So then this process heat is an endothermic. So the heat is being absorbing heat. And which formula to use in this portion here? This portion here, the temperature is changed, right? From zero, from minus 50 to 0. So here we are going to use this formula here, right? QMC delta T. That's the same formula here, but I just wrote in before. See. Then this portion here, that's melting, right? Here, the delta T, so the T is not changed. If it is not changed, we are not going to use this formula. We are going to use this formula here, right? In that case here will be enthalpy. The Q is equal mole numbers times enthalpy of fusion, right? Because he is changing. So it's the ice melting. The ice melting is what's actually fusion. So heat is equal mole numbers times enthalpy vaporization, and the enthalpy fusion here. Then when you go from water heating, that's going from changing here, right? From liquid to vapor, this process here, the water heating is endo or exothermic. So is the process increasing heat or decrease? So the heat is going this direction here, right? Increasing. So here you have is a endothermic. And which formula gonna answer use it to calculate this, the heat added this portion here will be Q, right, equal MC delta T. Because this portion here, you have what? You have the temperature is changing here, right? In that case, from 0 to 100. So yes, we are going to use this formula here, right, for this portion. All right, okay. Then next one, you have water boiling. Water boiling here, the delta T is not changed, right? If it's not changed, which formula I'm going to use here? There's one, right? Here, in changing from liquid to vapor, right? So here gonna be the Q is equal N enthalpy change or fusion here. Oh, sorry, vaporization here, right? Then here you have this one from the steam process, right? Here, which formula we're going to use here? We're going to use one that it has delta T, because here you have a delta T. The temperature change, right, from 100 to 150. So here would be the Q equal MC delta T. And is the process what here, endo or exo? Heating is going up, right? It's added, so he'll be endo as well. Right, now let's go backwards. Let's go going down here. So here, the coolest steam, right, steam cooling here, the temperature is increased, so while the heat is decreasing here, so here you have what? Endo or exothermic process here. You have exo, right? Because here it's losing heat. So you have exothermic process. And then all this process going down here will be all exo, right here. From gas to liquid, from liquid to solids, you have exothermic process, all right? Okay, there's a question here. I'm going to answer in the review here. Right, and then the phase diagram here. A phase diagram is a graph showing states of matter on conditions of temperature and pressure. It also shows change of state at triple point and critical point. Right here, sourcing here, the water phase diagram here, the water diagram here, you have this portion here that's only gas, here is only solid, here is only liquid, and then you have a supercritical point. So in this triple point right here, this one, you have a condition that you have solid, liquid, and liquid, solid, liquid, and gas at the same time and together here, right? And then this one shows the changes, right? State change, right? sublimation, right, from solid to gas, deposition from gas to solid, and here, liquid to gas, we have vaporization, and from gas to liquid, we have the condensation, and then melting is from solid to liquid, and then liquid to solid is freezing. Okay, so melting can also be called fusion, right? Okay, so the liquid interfaces, they start at triple point, at which all three states are in equilibrium and ends at the critical point. So above which the liquid and vapor are indistinguishable from each other here, the critical point. So cannot say which one is which here, vapor and liquid. So each point along this line is a boiling point of a substance at that pressure. The interface between liquid and solid marks the melting of a substance at each process. So below the triple point, the substance cannot exist in the liquid phase, right here. Below here, it's solid or gas, but not liquid. And along the solid gas line, those two phases are in equilibrium, and the sublimation point at which pressure is along this line here. So along this one here. Right. Then we have supercritical fluids. We have here the gas liquefy when pressure is applied. The temperature beyond which gas cannot be compressed is called the critical temperature. And the temperature needed to compress the liquid at critical temperature is called critical pressure. And the extent beyond this process here is supercritical. Beyond this temperature is called supercritical. Right, and the last topic here, so this diagram of water, the phase diagram of water that we have here, right? This area here will have the solid from this portion here. Water solid, like H2O, right? Solid here at this temperature and this pressure. So, and then from this temperature here, at this condition here, all gonna be what here? Gas, right? And the liquid have it right here. So now that the high critical temperature and the critical pressure, they are due to the strong van der Waals forces. So the water, right? H2O. Which intermolecular forces we have in H2O here, right? Let me draw here. I'm not going to write the electron dots here, the electron, I just don't get confused with these dots. So the oxygen will be the negative one, right? And the hydrogen will be the positive one. Right, so have the attractions between the positive and negative attractions here. So H2O, what special force do we have in H2O? First, right, all molecules, they have what? The special force, right? Oops. Okay, then you have the permanent dipoles, right? So yeah, also have a dipole. Because we have permanent poles. But we have a special kind of dipole. Which one it is? Are you seeing oxygen doing in the molecular force with hydrogen, right? Hydrogen bond